this one. Okay, simple beam with concentrated load at the center. Okay, our beam has span of 6 meters, right? And the point load P equal to 10 kilonewton. Okay, so it said that the reaction R is equal to P divided by 2. So R equal to P divided by 2 equal to 10 divided by 2 equal to 5 kilonewton. Okay, this one is the same as our calculation. Okay. About the shear force, this shear force V equal to the support reaction, and then you can see we get the same value, okay, without cutting the beam. And for the bending moment, we have this shape. We know that is 0 at the end and is maximum at the center or at the point load P. Okay, so the moment equal to P L divided by 4. Okay, P is our point load, so 10. L is the beam span equal to 6 divided by 4 equal to 10 times 6 divided by 4 equal to 15. 15 kilonewton meter. Like this, you get this one 15 kilonewton meter and phi n equal to 0. So I introduced you the table so it can help you to analyze structure more easily. Okay, like this. Okay, and for this one, I recommend you to memorize just this one. Okay, this one is we use very often. Okay, add more page. So if we have the uniformly distributed load all over the length like this, so maximum bending moment must be equal to omega multiplied by L square divided by 8. This one. Okay, for example, beam span of 4 meter and distributed load of, let's say, 2 kilonewton per meter. Okay, so this one omega equal to 2 kilonewton per meter and L equal to 4 meter. So maximum bending moment equal to omega L square divided by 4. So 2 kilonewton per meter multiplied by 4 meter square divided by 8. Oops, sorry, this one must be 8. So 2 multiplied by 4 square divided by 8, 4 kilonewton meter like this. Then most of the beam will be in this shape. So to determine maximum bending moment for shear, for bending state calculation is also easy. Okay, M max equal to omega L square divided by 8. Okay, this one is simple beam plus uniform distributed load. Okay, this one is common beam. Like this. Okay, like this. Then it's come to our last topics, which is the beam stress. Okay, I would like to add another look at this one. So you can see that the maximum bending moment is equal to omega L square divided by 8. In the other word, if you increase the span length by 2 times, you not double the maximum bending moment. You increase it 4 times because double span length if you double the span length, so m equal to omega, and you double the span length like this. So it will be 4 omega L square divided by 8. So omega L square divided by 2. As you can see, you increase the bending moment by 4 times if you double the span. In the other word, if you have many architecture would like to has longest span as possible. Longest span as possible. But we engineer if we add one support at the middle of the beam. If we add another support, we can cut the moment by 4 times. Let me show you a calculation. For example, an architecture, they would like to have very long beam, let's say 8 meter in span, and we have load of 2 kilonewton per meter, like this. So actually, the maximum bending moment is equal to 2 multiplied by 8 square divided by 8. Okay, so 2 multiplied by 8 square divided by 8. 16 kilonewton meter. This one is the maximum bending moment of 8 meter of beam span. But if possible, if we can add another support here, the bending moment can be analyzed by cutting it in half. Okay, so this one is 4 meter. Is 4 meter. So moment equal to the uniform load is the same, 2 kilonewton per meter. So 2 multiplied by 4 square divided by 8. So this one will be just 4 kilonewton meter. As you can see, 4 times different. Okay. I would like to show to you that to double the span length, the material cost would not be double. It will be 4 times higher. Yeah, so please manage the span length as efficiency as possible. I know that sometimes we need very long span as for the scenery or as the schematic of the building, but if possible, if we can introduce a support, it can help the structural size. It can save the material cost a lot because we double the span, we increase the load by 4 times, and then we roughly, if we analyze that state is equal to mc over I. If you increase the magnitude of moment by 4 times, that means you need 4 times bigger the size of the member. That is not maybe sometimes not an economical choice. Okay, please connect to this one. Please connect the knowledge of design. Okay, last one is the beam stress. The beam state is governed by the bending stress. Okay, this one is bending stress. Bending state is m. Actually, is my over I. Okay, because if we have beam like this with uniformly distributed load, if we cut the beam section, we will get Okay, if we cut the beam here, at the top of the beam, there will be compression. Okay, compression, and at the lowest of the beam, there will be tension, and at the neutral axis or the centroid, there will be no either tension or compression. So we will get the distribution of internal state like this. Okay, compression and tension. Okay, like this. And but when we design, we not design at any point. We design the maximum one. So this one is our wine. Okay, this wine is if the point of analysis at the neutral axis or at the centroid, so there will be no stress at all because there is no force here. But the stress will be maximum at the far end of the section. Okay, that one we not usually use parameter y, we use parameter c. The farthest one from the neutral axis to the top or the bottom of the member. So we can say that the maximum bending stress equal to maximum bending moment multiplied by c. Okay, the farthest length from the neutral axis to the edge of the member to over I. Okay, the moment of inertia of the section, like this. Okay. For example, I will use this. For example, I will use simple beam with uniformly distributed load. Okay, let's say 1 kilonewton per meter with span length of 4 meter. I would like to know how much maximum bending state of this one. Okay, and I have to design the section. So this section is a rectangle of, let's say, 5 centimeter by 10 centimeter. Too small. Let's say 5 centimeter by 10 centimeter. Okay. First, we need to know in order to find the bending state, we need to know maximum bending moment C and I. This case, maximum bending state equal to omega L square divided by 8. So this one is 1 kilonewton per meter. L is 4 square divided by 8. So we get 1 multiplied by 4 square divided by 8 equal to 2 kilonewton meter. If you don't want to use this formula, you have to cut the beam and analyze. I already teach you. But in the exam, I already give you this kind of table. Okay, so you can reference this table and use the formula directly for your convenience. Once you know the maximum bending moment, now you have to know the C and the I. C is from the neutral axis or at the centroid to the far end. So this one is rectangle, so it's easy for you to determine. Okay, so the farthest end is 5 centimeter. Okay, 5 centimeter. So in this case, C equal to 5 centimeter. Okay, but this one is the neutral axis. And for I, this one load is acting to this direction, so we need to know the let's say xy direction is setting like this, so we need to know the ix. Okay, ix equal to bh cube divided by 12. So b is 5 Okay, 5 H is 10 cube divided by 12. So 5 times 10 cube divided by 12. 416.67 centimeter power by 4. Okay, now we get everything we need to know about the bending state. So bending state equal to max. Okay, maximum bending state equal to max maximum bending moment multiplied by C over I. So 2 kilonewton meter, but I and C in centimeter, so I think it's more convenient for me to convert from meter to centimeter. So okay, I will convert the unit here first, and then multiply by 5 centimeter. Then this one can be cancelled. I is 416.67 centimeter power by 4. Okay, then 2 divided by 100 multiplied by 5 divided by 416.67 equal to 2.340 minus 4. This one will be kilonewton per square centimeter. Okay, kilonewton per square centimeter. Like this, we can get the bending stress of this beam. Okay, and then to use this bending state, we have to compare it with the allowable stress. Okay, allowable stress. Okay, for working state design, this allowable state equal to 0.6 of yield strength of the material. Okay, and for the yield strength of the material, you have to refer to the catalog. Okay, in catalog, there will be spec of this yield strength. Okay, this one, yield strength. There are many grades. So we as a designer, we select this grade. Okay, which one we would like to use, and then we compare it to the design. Okay, let's use the cheapest one, SS400. So yield strength is 245 Newton per. Have a better capture this one. Okay, assume using SS400 steel as a material. So the yield strength equal to 245 Newton per square millimeter. Okay. So allowable state equal to 0.6 of Fy equal to 0.6 of 245 equal to 147 Newton per square millimeter. Actual stress we already calculate as 2.0 or 2.4, sorry. 2.4 kilonewton per square centimeter. But the unit is different, so we have to change. So 2.4 from kilo is 2.4, sorry. 2 kilonewton per square millimeter. Oops, square centimeter. Sorry. Okay, 2.4 multiplied by 10 power by minus 4 kilonewton per square centimeter. 10 minus 4 kilo is 10 power by 3, then just Newton. So this one is square centimeter. Square centimeter. Let me write it down here. So centimeter square is actually centimeter square. Okay, so centi is 10 power by minus 2 meter square. Like this. So it's equal to this one. Okay, equal to 10 power by minus 4 meter square. So 10 power by minus 4 meter square. But we need this one in terms of millimeter square. Let me change. Okay. Oops, sorry. We need millimeter square. So let's change this calculation a little bit. Okay, centimeter square equal to centimeter square. And then we will change this one inside centimeter. 1 centimeter. 1 centimeter equal to 10 millimeter. Okay. Okay, meter square. Okay. 1 centimeter equal to 10. 1 centi equal to 10 milli. Then we cancel this term. And so 1 square centimeter equal to 100 millimeter square. Okay. Might be correct. Let me check. 1 centimeter square. Okay, correct. 1 centimeter square equal to 100 millimeter square. So we just multiply 100 millimeter square. Then we will get the actual stress. 2.4 multiplied by 10 power by minus 4 multiplied by 10 power by 3 but divided by 100. 2.4 multiplied by 10 power minus 3 kilonewton per millimeter square. So this one is indeed absolutely past the criteria. Okay, like this. So I think my load may be too small for this case. But it's fine. Okay. Like this is the way we design. So the design is acceptable. The design is in accordance with acceptable bending state criteria. Like this. Okay, and another thing is that there is not only the bending stress, there is also the shear stress we have to concern. Okay, the shear stress denoted by V. This one is equal to P divided by 2, I think. Let me check first. for rectangle, 3 multiplied by V divided by 2 multiplied by A, where V is the shear force and A is the section area. Okay, and most of the beam is rectangle or wide flanked. For wide flank is let me check the formula. Okay, equal to V. Okay, a moment. Let me check the material first. Beam state. Okay. Okay. Usually use this one. Okay. For the wide flank beam, you would V divided by thickness of the web multiplied by the depth of the beam. Okay. Yep. V divided by thickness of the web multiplied by D. Okay, like this. Beam depth. Okay, like this. Okay, in our case, our beam is rectangle beam, so shear stress is 3 multiplied by shear force. Okay, shear force we haven't calculated yet, so let's say V equal to omega L divided by 2. This one is according to the V equal to omega L divided by 2. 1 kilonewton per meter multiplied by span 4 meter divided by 2. So 2 kilonewton as the shear force. So shear stress equal to 3 multiplied by shear force 2 kilonewton divided by 2 multiplied by sectional area. Area of our beam is 5 centimeter by 10 centimeter. So I will convert it to let's convert it to the Newton per square millimeter for our convenience of comparison. 2 times of sectional area, so 550 millimeter multiplied by 100 millimeter. Then T multiplied by 2000, 250, 100, 0.5 Newton per square millimeter, like this. Okay, this one is the shear stress. Okay. Let me check this one. Kilonewton meter. Okay, correct. Kilonewton meter, kilonewton centimeter. Let me check the unit conversion first. kilonewton per centimeter square okay, properly correct. Okay, like this, and then for the shear state criteria we can check. Okay, so this one is just 0.5, but our material can withstand up to 245, so it's automatically can be passed in the criteria like this. Okay, in my exam I will ask you about the usage of this formula. Okay, and how to link this knowledge with other parameter. Okay, it will be conceptual check, but if you would like to calculate, sure, you can calculate in order to get the result. Okay, like this. And for detail, you can check in our class material. I already explained how to calculate and how to compare, how to design. Okay, concretely in this calculation, you can have a quick look here. As for today, who has any question or any concern ครับ about our exam?
No problem. Can you send the recording ครับอาจารย์
Yeah, sure. I will send the recording together with this paper to you.
Thank you so much ครับ
Okay ครับ so I hope you good luck in the exam, and before the exam, if you have any question or you encounter any problem or any difficulty, you can directly contact me. Okay ครับ thank you so much for your attention and have a good Sunday ครับผม
Thank you ครับ Have a good Sunday ครับ